the E-type model, you can see that the column in the one story, it has been replaced with the size of 24/24 with FC prime, same data of the retaining wall. If you right click on it, this is 24/24, and 3 psi was the FC prime for the retaining walls. Next thing I want to share with you that whenever the shear wall thickness is greater than that of the beam, then you can remove those columns at the end of those shear walls and lift walls. So I have removed these walls. You can see in here I have removed this column and this column. I have also removed column from this grid, from this, because whenever you have a column very adjacent or very near to the walls, structure walls, so because of this higher stiffness, it attracts more lateral forces. So the column will be overstressed. So due to avoid this problem, it's better to remove the column from these grids and increase the thickness of the shear wall if your shear wall is not working or it is overstressed. So you can see that I have removed these columns, right? Because we have taken the thickness of the shear walls and lift walls is 18 inches, which is greater than the beam width, which is 15 inches. We have discussed that. Now, the new topic is the load patterns, and it can be several load patterns if you are designing a structure for the in the area when there is no seismicity, then you have to define a different type of loads. When you are designing your structure for tsunami, and then the load patterns will be different. And if you are designing your structure for the gravity loads, the load patterns will be different. But when you are designing your structure for the seismic plus gravity, then the load patterns will be different. So in our case, we will define these 5 load patterns, which consist of the dead load, which will be the self-weight. Second will be the SDL, which is the superimposed dead load, which will be the weight of the PCC, tiles, marbles, and the partition walls. And the third one is the live load. The fourth one is the earthquake load in X direction, and the last one is the earthquake load in the Y direction. Now, the first one is the self-weight of the members of the building. And for the self-weight of the structure members, you have to select the type as dead. You can name it load as dead. You can see in here in this figure. And the self-weight multiplier is 1. It means it will multiply or take the density, by multiply the density of the material with the length, height, and thickness of the member, and it will calculate the weight of the member for you, right? So the self-weight multiplier should be 1 only for the dead, for the self-weight of the building. Note that if you keep this factor as 0, software will not calculate the self-weight of the members, right? So this should be 1 in case of only dead type load pattern. The second is the live and super dead loads. And for the live and super dead loads, superimposed dead loads, then you have to select the desired, you can name it live. You select the type is live, and the self-multiplier of weight should be 0. So if you multiply this, take this factor as 1, then software will calculate the weight of the members based on the live loads and as well as on the dead loads. So it will also multiply that we have applied the load, live load, for example, 40 PSF. So it will calculate the weight of the structure, and it will multiply with the weight of the structure into 40 psi and the load will be doubled. So it will not be correct. So for the live and super dead load, the self-weight multiplier should be 0. So we'll go to the E tab. We will go to the define load patterns. In the default template of the E tabs, these two will always be defined. The dead load, which is type dead, and the self-weight multiplier is taken by default as 1 by the E tab, and the second one is the live. So you can change it, the name of this, for example, live load, and click on this modify load, and the type will be this one. You can select dead load, super dead, live, roof, in the seismic and wind and snow construction. And if there is not defined in this, so you can select the other. So in our case, it is live, it is live. Now we will define the SDL, which is the super dead load, superimposed dead load. We will name it as SDL, and we will select the load type is super dead, and we will add new load. So this load pattern has been added. So whenever you define a load pattern, in the background, the ETABs automatically generate load case for these load patterns, right? If I click OK and go to the load cases, you can see that the load cases for the dead, live, and SDL, it has been generated automatically by the ETAB. Next is the earthquake load pattern, and it is same as of the live load in SDL, that you should keep the self-weight multiplier as 0 and select the desired code. For example, this is ASC716, and click on the modify load pattern, and then you have to insert the earthquake load parameters, and you have to take those parameters from your desired code, which is, for example, if you're designing your structure in Pakistan, then you have to take the data from Building Code of Pakistan 2021. So when you open the lateral load, modify the lateral load, so this tab will appear, and we will discuss that. So let us define load pattern for the earthquake, and we will name it as earthquake in X. We will select the type as seismic, and from the auto lateral load, we will select ASC716. We will add new load. Similarly, we will define it as in Y direction, the same load type, the same code, add new, and now we have to click on the EX modify lateral load. So this tab will appear. So now we will discuss this tab in the PowerPoint, and we will come again. So the first one is the direction and eccentricity. Then you have to check the direction for which you want to define this load pattern. And you have to insert the eccentricity, accidental eccentricity, which is 5%, and it is 0.05, which code allows you to take it in the design of the seismic. If you are designing your structure for the seismic loads. The next is the time period. There are different options available. You can calculate the time period using approximate method, of you want the program to calculate the time period for you, or you can add the time period as your value is user defined. You can add the time period of the building by manually. And the next one is the story range. You can get this information from the table 12.8.2.1 of ASC716, which is coming up in the next slides. And the next is the story range, which you will tell the ETAB to insert or apply the lateral forces from this story to up to this story. So that will be the range of the seismic loads. Next is the seismic coefficients. and it is 0.2 second spectral acceleration SS value, 1 second value, and this is long period transition, which is not a significant effect on the buildings, but on the conservative side, you can put the value of 8, and you can take these values from the maps or the table of your design code. Next is the site class, and this can be classified in this table, but normally this information will be given in the use technical report. And it will automatically calculate the SDS, the design spectral acceleration for you, right? So these are the values. The other factors includes the response modification factor R. Actually, R is the redundancy, that how much your structure is redundant. Greater the value of R, more toughness and resilient your structure is. Less the value of R, more shear force will produce, base shear to produce, and the structure is less redundant. The system overstrength omega is actually used when you want your specific members or columns not undergo inelastic behavior to remain elastic throughout its life. So you, in that case, the omega will be used. And the deflection amplification factor CD is used in the calculation of the inelastic drift. And the last one is the occupancy importance factor, which is the IE, and you can get this information from table 1.5-2. And for the other factors, R, omega, and CD, you can visit table 12.2-1. So the seismic factors, for example, we are designing this structure for the Peshawar district. So the SS value is 0.8399 and S1 value for the 2% probability of occurrence in 50 years. And the S1 value is 0.243. The importance factor, IE for the seismic importance factor is 1.25. And the time period parameters CT and X. This is the structure type, this is CT, and this is X. This is actually these values are used in the calculation of the time period of your building. So for the moment resting frame, in which all the forces will be resisted by the frame. So for the steel, these values are 0.028 and 0.8. And for the concrete, it's 0.016, 0.9. And for all other structures, which includes the building frame system, bearing wall systems, and also dual system, the values is 0.02 and 0.75. So we'll insert these values 8399. So we will go to the define. We will uncheck the y direction. What does it mean by these three values? So the tape will first apply the seismic forces in the x direction without eccentricity. This will be the first one. You will get the seismic forces 3 times, 1, 2, 3. The second time it will multiply, it will apply the load in the x direction with plus eccentricity, and at the third time it will apply the seismic forces in the x direction with minus eccentricity. So we will get 3 values of the base shear, and normally if there is no significant change, these values will be identical. This overrides eccentricity is actually used in the amplification factors, and we will discuss later on this. Now we will add the seismic coefficient values, which is 0.8399, and you can take SS value is 0.29, and this period is 8. We will take a site class SD, because the code allows you, and you do not have any soil data, then you can take the site class SD. So you can see that it has calculated these factors for you. The response modification factor R, we will discuss that. So we will use the approximate And in our case, we have 0.02 and 0.75. That is CT, and this 0.02 is the value of CT, and 0.75 is the value of X. And we will apply the range from basement 2, which is actually the end of the retaining wall, up to the 18th floor. We will take it as 7. If I remember, this was 2.5 and this is 1.2. I click OK. Similarly, I will show you in the table as well. This is 0.275. This is 0.8399. 0.29. This is D. 7, 2.5. So I have taken this value 0.02, 0.75, insert this value, insert this 1.25, and this is the table where you will take the response modification factor R values or strength factor and amplification factor. And this will you can find it in the dual system, as we are designing our structure as a dual system with special moment frames capable of resisting at least 25% of the described seismic forces. And we are using the third one, special reinforced concrete shear walls. So the R value is 7, or strength factor omega is 2.5, and CD is 5.5, and there is no limit in the height of the building. So this was the whole story about the load patterns. If I go again to the load cases, that you can see that, which I have explained earlier, that when you define a load pattern, it automatically defines and generates the load cases for that load pattern. You can see that RPX is a linear static analysis. If you modify this, you can see that it is defined as a load. So it will be applied as a load. And in case of the time history analysis, you will have to select the X direction. A load combination. So these are the load combination which is defined in the ASC 716, and ACI refers you to this code that you define the load combination as per the ASC, because ACI is using this load combination taken from the ASC 716. These are the different load combination which consist of the earthquake, gravity, and wind. So when you do not have any wind load case, so it will not generate any load combination that contains. It has also care of the vertical effect of the earthquake, which is 1.2 D plus EV plus EMH plus L into 0.2 S. If there is no snow, so it will become 0, and it is 0.9 D minus EV plus EMH. H is M, for example, H means horizontal and V means vertical. So ETAP automatically generate and incorporate these load combinations. You can define your own load combos by calculating the different factors that you have to multiply in the load combination, but ETABs generate this. For example, let me delete this. You can add, for example, 1.2 D plus 1.6 live. So you can add 1.2 D, which is the dead load self-weight. This is SDL. So this will be 1.2 and this will be 1.2. And you can add another live as 1.6. Right, so in this way, you can generate your own load combos, but there is an option, add default load combos, and it will generate your load combination as per the design code you have selected. And you have to select the design code from this design, repeat frame design, view revise references. From here, you have to select the design code. If you want to select ACI 31819 or Chinese code or Indian code, European code. So it will generate the load combination as per the design code you have selected in this tab. So go to the load combination, add the file load combos, select concrete frame design, concrete shear wall design, and concrete slab wheel design slab actually in the slab. So convert into the user combination editable, click OK. You can see that it has generated the load combos. You can see that if I click on this modify, you can see that it is 0.8 dead, 0.8 SDL, and 1 EX. And if I go to here, you can see that the combination, the last one is 0.9 D minus. So in the combination, it was 0.8 D because the vertical effect of the earthquake is always subtracted from the dead load case. So it has calculated the vertical effect of the earthquake as 0.1, and it has subtracted from 0.9 D, and it defines load combination as 0.8 for you. Right? So it is 0.8. The original it was 0.9, but it has subtracted the vertical load effect. So it will give you final load scale factor is 0.8. So this is the for gravity is 1.2, 1.6, and 1.2. This is another load factor, load combination, and these are the scale factor, which is 1.3. It is also calculated the factors from here. You can see that the sixth one, it is 1.2 D plus P plus H plus L. And this time it has added the effect of vertical effect of the earthquake. So it was originally 1.2 D. By adding this as 1 or 0.1, so it becomes 1.3. So you can see that it has defined a load combination with a scale factor of 1.3. So this is how it calculates different scale factors for the load combination. So you do not have to do it manually. Defining load cases. Load cases are automatically generated by program, which I've explained and showed you earlier. The next is the response spectrum case, and there are several analytical procedures available in the code, which is present in the ASC 716 table 12.6-1. If you do not want to use the response spectrum case, it's your choice, because there is no limitation on any of the analytical procedure. For example, the first one is the static linear procedure, which is equivalent lateral force procedure, and it is permitted in seismic design category B, C for all structures, and it is permitted for the D and F for the S category 1 or 2 building not exceeding 2 stories, and there is a limit on the structure height. Structures with no structural irregularities and not exceeding 160 feet in the structural height, so we can use the equivalent static force procedure. For the structures not exceeding 0.6 structural heights and having only horizontal or irregularities, you can also use the static linear procedure. And for the all other structures, it is not permitted. For example, elevated water tanks in the high seismic areas and many other structures. The next one is the model response spectrum analysis, which is a linear history, which is the response spectrum analysis, which uses model analysis. It is also permitted in all of the cases in all of the seismic design category B, C, D, F. And the last one is the nonlinear response history analysis, which is time history analysis, and it is permitted in all of the structural characteristics. So we will be using the response spectrum analysis in order to have an idea, or you get familiar, because the future is for the response spectrum case, because in the new code, there will be several limitations, and there are some limitation on the equivalent lateral force procedure. So for the linear dynamic analysis, which is the response spectrum analysis, there are different requirements that you have fulfilled if you are using this method. That the analysis shall be conducted to determine the nature and mode of the vibration of the structure, and for the analysis shall include a sufficient number of modes to obtain a combined model mass participation of 100% of the structure mass. Right, so this condition should be fulfilled, that the mass participation factor should be 100% of the structure. There is also an exemption. Alternately, the analysis shall be permitted to include a minimum number of modes to obtain a combined model mass participation at least 90% of the actual mass in each orthogonal horizontal direction of the response constituted in the model. For the scale factor, initially, what will be the scale factor in the response spectrum case? And the code defines that you take the scale factor I into G divided by R, and I is actually the seismic importance factor, G is the gravitational acceleration, because the response spectrum is curve is always in the G format. For example, it is 0.29, it means 0.29 G, right? Gravitational acceleration. So when you convert G units into inch units, then you have to multiply it 383.4 into 1.25 and divide by the response modification factor, which is R. So the scale factor initially is 68.4. Right, so this is actually the theory of this, which I've explained it, so you can read it out. We will go to the E tab. We'll go to the load case, we'll click on the add new case. We will name it as response spectrum analysis, RSA. In X direction, and we will select the load case type as linear static. For the earthquake in X and Y. For the RSA, you have to select, this is actually linear static used for the ELF method. This is for the calculation of the deflections and the push-over analysis. This is the time history analysis. This is the response spectrum. So you have to select the response spectrum case. This because you are defining the response spectrum. And for the loads applied, click on the 8. The mass source is actually taken from the previous, which is defined as default by the ETAB, and we will discuss in a few minutes. So this time, the load will be acceleration, because you are using response spectrum, and response spectrum is actually accelerations. You are applying acceleration to the building instead of forces, which is applied in case of the ELF method. And the load name is U1. U1 means the X direction, U2 means Y, U3 means Z direction, translation. R1 means rotation in the X direction, rotation in the Y direction, rotation in the Z direction. So we are applying a straightforward force, which is the translational force, acceleration, and that will be U1. And the function that you have defined, you have to select from here. So let's first define the function. I'll go to define, click on the function response spectrum, and choose the function type as ASC716, and click on the add new function and name it RSA. Just simple RSA. The damping ratio will be 5%. You can change it as per your requirement, and this information should be same as you have used in the linear static procedure 0.2. This is add, this is D, and the curve has been defined. So you can see that this the vertical is the spectral acceleration in terms of G, and on the horizontal there is time period. Click OK. So this function has been defined. Again, go to the load cases, add new load case. Click on the RSAX response spectrum, add acceleration in X direction, select that function RSA, and the scale factor should be 68.4. This is the initial scale factor. The model load case will be model. It will use the eigenvalues, and the model combination method will be SRSS, square root of sum of squares. And the direction combination will always be taken as RSS, which is square root of sum of squares. And the model damping is 0.5, and the diaphragm eccentricity that if taken 5%, we will also take is 5% for all the diaphragms. Right, 0.05 for all the diaphragms. Click OK. Now again, take copy of this case and name it RSA Y direction. And this time select U2 and keep all the data is same. So this has been defined. Now again, go to the load combination. Now the load combination do not contain any response spectrum case, so you have to select all, delete these. Add default combos, complete shear walls converted into user defined. And now you can see that it will define the response spectrum case same as of the linear static procedure, because you will use this combination for the final design of your structural members. So this is the whole story about the response spectrum. The mass source, only dead loads are to be used in the calculation of the seismic weight of the structure, and it is defined in section 12.7.2 that effective seismic weight of a structure shall include dead load as defined in section this above the base, or other loads above the base as listed below. And normally the designer takes 25% of the live loads, but it is only applicable in case of the storages. For example, it is a warehouse, then you have to take 25% of the live load as well in the mass source. So we will go to the E tab and we will define the mass source. We'll go to define mass source. Click on the modify, and this is name given by the E tab. And you can click on the element self mass, so it will only calculate the weight of the structure for the self weight of the building, self mass, right? So we want the non-structural elements, for example, partition walls, to be included in the calculation of the mass source. So you have to insert only dead load and STL modify. So these two loads should be, and keep this as default. Keep these two values, load patterns in the mass source. And if you want to define live load as well, in case of the storage purposes, warehouses, so you can add 0.25, and this factor should be 0.25 in case of the live load. So we delete this. This time we click OK. This was the whole story about the module 3.